Hello world. What the heck?
Togon.
Okay, so time to actually do the hypergeometric function like I said I was going to do. Just had to close my door so the dog doesn't get in. So in the last video I actually made a couple of kind of egregious errors that I need to correct at the beginning. And then we're actually going to start talking about the regular hypergeometric function. We will discuss its derivative, we will discuss certain properties of it, and how it's based on rising factorials. And we will come up with some functional examples of what happens when we plug in certain values for the bases of those hyperfactorials. Okay, so mistakes I made last time. Well, so the first one that I think I should highlight was this claim right here, that 1 divided by the nth rising factorial of x is equal to the nth power of -1 times the nth falling factorial of 1 minus x, and likewise that 1 over the nth falling factorial of x is equal to -1 to the nth power times 1 minus, I keep saying this part first, the nth rising factorial of 1 over x. And it's quite obvious when you see this that this cannot be true, because this is an nth degree polynomial, and this is the reciprocal of an nth degree polynomial. Oops, the shadow is pretty bad. I hope that's visible. So what this is saying is that an nth degree polynomial is equal to the reciprocal of an nth degree polynomial, and that's of course impossible, since that's like saying something that's got a degree n is the same as something with degree 1 over n. And that's just simply not possible, and this is essentially just what you get when you plug 1 minus x into the first one, and so they're sort of just interchangeable, and so clearly that can't be right. Those are not equal to each other, and that was a false statement. What is correct is just the regular relationship that I derived in the other one, relating them based on a power of -1 and what happens when you plug in the negative of the base. So defer to that. The other thing that I said was correct and is not is using this fact here, that the m plus nth rising factorial of something being equal to the mth rising factorial of x times the nth rising factorial of x plus m. I tried to use this to say that the 2nth rising factorial of 2x is equal to 2 to the 2n times the nth rising factorial of x times the nth rising factorial of x plus n over 2. And the thing that's wrong with this is that this should just be 1, not n, inside. It shouldn't be n over 2, it should be 1 over 2. So this is not true. This is, but for some reason, I'm not really sure why, this does not jive with this. I don't really know why, to be completely honest with you. I think it has something to do with factoring out the powers of 2, and I think that if it were x to the 2n, then, you'll see that the other thing has to be correct just by analyzing it. So if we consider what this is going to be 2x times 2x plus 1 times 2x plus 2 times 2x plus 2n minus 2 times 2x plus 2n minus 1. And this is the 2nth rising factorial of 2x. And what you want to do is you want to first consider all the even terms, so all the ones that are clearly even numbers, so 2x, 2x plus 2, 2x plus 2n minus 2, and all the stuff in between. And essentially what you want to do is you want to factor 2 out of all of those, so that's going to be n factors of 2. And then we're going to get x times x plus 1 all the way up to x plus n minus 1, which is of course the nth rising factorial of x. And so that's where that part comes in. So we've got half of these, we've got this, and now we just need to derive this and the other n powers of 2. And essentially that comes from looking at the odd terms, right? So there's all the odd terms, there's 2n plus 1, 2n plus 3, 2n plus 5, etc. And essentially it's also going to be n terms, and when we factor out a power of 2, we're again going, from each of them, we're again going to get another n powers of 2, and we're going to have x plus 1 half times x plus 3 halves times x plus 5 halves, all the way up to x plus 2n minus 1 halves. And that is, of course, the nth rising factorial of x plus 1/2. And so this simplifies to be 2 to the 2n, just by combining these two together, times the nth rising factorial of x, times the nth rising factorial of x plus 1/2, and so this is a neat little duplication formula for rising factorials, and it is not this. So the only difference here is that this is not an n, this is a 1. So this is not true, and this is. I guess the one time I actually corrected Wikipedia, I let that go to my head a little bit. My bad. So with the corrections out of the way, let's start talking about the hypergeometric function. So the hypergeometric function is a function defined in terms of an infinite series. It's like a Taylor series. It's got a bunch of coefficients with powers of an input. And it's defined for more or less any complex number you want, as long as it's within the circle of radius 1 centered at the origin. So this is usually written like so. So we have f with a little subscript 2 on the left and a subscript 1 on the right, and I'll explain why. And then we have an input A, an input B, then a semicolon, then an input C, then another semicolon, and the independent variable z, or z, if you are more cultured. As an American, I'm insulting myself, you see, that's the comedy of it all. And so essentially these are just sort of numbers you pick, and you can pick them to be whatever you want, honestly, and z is like the variable. So this is defined to be the sum from n equals 0 to infinity of the nth rising factorial of A times the nth rising factorial of B divided by the nth rising factorial of C times z to the power of n divided by n factorial. And so why is this a 2 and a 1? This is a 2 here on the left because there are two different inputs before the semicolon, and this is a 1 on the right because there's one input here between the semicolons, and then the z is always by itself. If this were some integer p, then you would have p different inputs here, like a sub 1, a sub 2, a sub 3, all the way up to a sub p. And if this number on the right were q, then you would have you would have b, in the second spot you would have c sub 1, c sub 2, c sub 3, all the way up to c sub q, whatever that is. In this case, there's only 2, so we just pick a and b, and there's only one in the second spot, so we just put a c. But in theory, you could have as many as you want, and that is the generalized hypergeometric function, having as many as you want. Notice that if these were both 0, then it would just be f of z, and we would just have the infinite series for e to the power of z. So the 0, 0 hypergeometric function is just the exponential function, e to the z. And you can sort of explore other combinations of this, and this is the most commonly used one, just because there's a little more variety to the combinations. You could do 1 and 1, you could do 1 and 0, it doesn't really matter. The point is that this is the most commonly referenced one, and in general, it's usually written like this, but just for the sake of brevity, I'm just not going to write the subscripts in this part. The only time I'm going to use the subscripts is if I'm talking about subscripts other than 2 and 1. Okay? So let's maybe explore this function a little bit. So you see we have a bunch of rising factorials in it. We should consider the properties of rising factorials that we are used to, or that we know from the previous video, so that we can determine some things about this. First of all, what we can see from this is that the first term in any hypergeometric function, no matter what a, b, and c you pick, is always going to be 1, because, I should say the 0th term, because we're plugging in n, and the 0th rising factorial of anything is 1. Z to the 0 is 1, 0 factorial is 1. So the first term is always 1. If you pick A or B, and by default we'll just go with A, because it doesn't matter which one you pick, they're perfectly interchangeable. So let's say we pick A, so let A equal negative m, where m is a natural number or 0. So any non-negative, so m is any non-negative number, we're multiplying it by -1, so we get 0, -1, -2, etc. So imagine negative m, let's pick m to be like 3, so we have -3. Let's see what the 4th rising factorial of -3 is. And that means we just add 1 3 times to this. So we have so this is just going to be -3 times -2 times -1 times 0. Boom, look at that. So if n is high enough, if the rising factorial is high enough for a non-positive integer base, then eventually that product will be 0, because eventually you're just going to count up 1 by 1 until you get to 0. Which is to say that if we pick A, and again by default A, without loss of generality, we could be picking B, it doesn't matter, but by default, but in general, if you pick a to be a non-negative integer, then this will have finitely many terms. It will go from n equals 0 to whatever m is, right? Because as soon as you go past m, you are multiplying by 0 because you've added up to 0. But we know if we have any negative integer, or 0, right, if we're at 0, we're starting there, so it's always going to be 0. But if we started a negative integer, and we have the power, or I shouldn't say the power, and I also wrote 4, I should have written a 4 with a bar above it to signify rising factorial. I'll call it the height of the rising factorial, if the absolute value of that number is first of all an integer, and it's bigger than the absolute value of the non-positive integer base, then the product will be 0. Because, imagine you have the mth rising factorial of negative m. Well, this is just going to be negative m times negative m plus 1 all the way up to negative m plus m minus 1. But of course, negative m plus m minus 1 is just negative 1, and the next step after that would be 0. So if we did the m plus first rising factorial of negative m, we would just be multiplying by 0 in the end, and everything goes away anyway. So the point is that if we define, or in particular, take f of negative m, comma b, and then semicolon c, and then the input z, what we end up with is the sum from n equals 0 to infinity, the nth rising factorial of negative n times the nth rising factorial of b divided by the nth rising factorial of c times z to the n over n factorial. But of course, we had another fact in the previous video that allowed us to relate falling factorials and rising factorials through powers of -1 and replacing the input with a negative number. So we recall that the nth rising factorial of m is equal to -1 to the n of the nth falling factorial of -m. And likewise, you can just swap those two things, right? The nth falling factorial of m is equal to -1 to the n times the nth rising factorial of -m, and they can be swapped. So essentially you just multiply that over and plug in -m, and you see that they can be swapped like that. The point of me doing that is because I can now plug in -m here, and that becomes +m, because I'm just plugging in -m wherever I see m. And notice that I can replace this, which is here, with this right here. And this is just -1 to the n times the nth falling factorial of m. And then we just have to recall how we can write the nth falling factorial of m using factorials, and that can be easily rewritten. We got to keep the -1 to the n there. But now remember, the nth falling factorial is like m choose n, but you're not dividing by n factorial, right? It's just m factorial divided by m minus n factorial. Right, so we can replace this nth rising factorial of -m with -1 to the nth power times m factorial over m minus n factorial. But notice we also have an n factorial in the definition of the hypergeometric function. So this can go with that down in here, like so, putting an n factorial down there, and notice that this is just m choose n, right? So if you, and I'm sorry, this should have been m at the top there, right? Because every term after the mth term is 0, so we don't have to include it. And we can just now replace this here, the nth rising factorial of -m, with -1 to the n times m choose n, and we get rid of this n factorial in the denominator there because it goes in to contribute to the choose function. So, using all those facts that we derived in the previous video, we now see that picking a or b to be a non-positive integer results in the hypergeometric function being able to be expressed like so. I guess technically we should write the infinite sign there because now we're transitioning to the finite case. So we have n equals 0 to m of -1 to the nth power times m choose n times the nth rising factorial of b divided by the nth rising factorial of c times z to the nth power. And so this is a neat little finite expression. It's a polynomial, right? It's a polynomial of degree m if you are to pick a or b as a non-positive integer, negative m. So if m is 0, of course negative m is just 0 as well, so that doesn't matter. We're assuming m is some non-negative integer, and then we're plugging in negative m, so we get a non-positive integer. And you end up with this finite polynomial here, which is I guess it's nonsensical to say finite polynomial. If it is a polynomial, it's finite. An nth degree polynomial, I should say. And so that's, you pick m to be 3, you get a cubic polynomial, right? Not too difficult. What should we do next? Let's see if we can deduce something about the derivative of the hypergeometric function. Of course, the derivative with respect to z, because that is the input. So here's our finite expression if we plug in a non-positive integer in for a or b. So let's just erase that. And now we're going to ask ourselves, what is the derivative of f with respect to z? So the derivative with respect to z of f. And this is, of course, a, b, c, and z. And naturally, we can just bring down the power, use the power rule, right? This is just, if this is well defined, and if this is differentiable, right, on the unit disk, then we can just apply the derivative to each of the terms, and we just use the power rule, right? The power comes down, the n comes down, cancels with the n here, and we're left with z to the n minus 1 divided by n minus 1 factorial. So of course that's pretty easy, but the point is to see how might we be able to manipulate this into being in terms of the original hypergeometric function. So we're left with the nth rising factorial of a times the nth rising factorial of b divided by the nth rising factorial of c times z to the n minus 1 divided by n minus 1 factorial. Because using the power rule, the n comes down, we get n minus 1 as a power, the n cancels with the n here, and we're left with n minus 1 factorial. Let me draw a better z. It was starting to look like a z. Oof, my god, terrible, just awful. That's better, still terrible. And now how can we maybe write this like the original hypergeometric function, right? Because if we can somehow rewrite this as n factorial in the denominator and n in the power of z, we can then take whatever we get as our base of the, what are they called? Rising factorials, and just sort of plug those in as the new a, b, and c in our hypergeometric function. And it's not too hard to see how we might do that. The first step to realize is that, remember what I said before, the first term of the hypergeometric function is always 1, because the 0th rising factorial of anything is 1, anything to the 0 power is 1, 0 factorial is 1, so it's always 1. Which means when we took the derivative of this, that first term can actually go away, because we never needed it, because it's a constant, right? It's always 1, and so the derivative of that is 0. So we're actually starting off at 1 and going to infinity. N equals 1 and going to infinity. So what we can then do is now replace n with n plus 1. So all of these n's are going to go up by 1, which means the index simply has to go down by 1. Infinity doesn't care how much you're shifted by. So then we're going to have that this is equal to the sum from n equals 0 to infinity of, now we have to plug in n plus 1 wherever we see an n, and we get the n plus first rising factorial of a times the n plus first rising factorial of b divided by the n plus first rising factorial of c times z to the n divided by n factorial. But notice this is still not like the hypergeometric function, because we have n plus 1 as the height of the rising factorials, even though we have regained our a, b, or we've kept our a, b, and c, but we want n to be in there. So how do we do that? We need to come up with some way of representing an n plus first rising factorial in terms of an nth rising factorial, and it's not too hard to see how you might do that. Consider the n plus first rising factorial of x. Well, this is just x times x plus 1 all the way up to x plus n minus 1, right? But notice if we just eliminated that first x, we would now have the, I'm sorry, this should be all the way up to x minus n, x plus n, my bad, because we're plugging in n plus 1. But if we got rid of the first x, this would just be the nth rising factorial of x plus 1, right? We just start off with x plus 1 instead of x. We obviously can't get rid of it, but what we can say is that this is therefore equal to x times the nth rising factorial of x plus 1. We simply just change where we're starting to count the rising factorial, and we just relocate it like that. And we can do that with a, b, and c. So what I'm saying is if we factor out a, factor out b, and factor out c, we can just write this as the nth rising factorial of a plus 1, as well as b plus 1, and dividing by that of c plus 1. And so because a, b, and c don't depend on n, we can just factor them out of the sum. And we have a times b divided by c times the sum from n equals 0 to infinity of the nth rising factorial of a plus 1 times the nth rising factorial of b plus 1 divided by the nth rising factorial of c plus 1 times z to the n divided by n factorial. I hope that was clear so far. And what is this? This is simply a times b divided by c times the hypergeometric function evaluated at a plus 1, b plus 1, semicolon, c plus 1, semicolon, and z. And so what does that tell us? That tells us that the derivative of the hypergeometric function with respect to z is simply a constant times the hypergeometric function evaluated at the same a, b, and c, but just plus 1 to all of those. And you can actually see how we might carry this forward. If we took the second derivative, what we'd have to do is simply, divide again, and then shift all the indices up by 1 again, and then we'll be doing the n plus first rising factorial of a plus 1. And we would just use this same fact again, pull that out, and then we would have the nth rising factorial of a plus 2, similarly b plus 2, and c plus 2. And then on the outside we would have a times a plus 1, b times b plus 1, and divided by c times c plus 1. And so that would be, if you carry that forward again and again and again, you derive the very interesting result that let's call it the kth derivative, so taking the derivative k times of f of a, b, c, and z is simply the kth rising factorial of a times the kth rising factorial of b divided by the kth rising factorial of c times the hypergeometric function f at a plus k, b plus k, semicolon, c plus k, semicolon, z. So if you take k derivatives of the hypergeometric function, you end up with sort of this thing on the outside, but instead of it being of the index n, it's of the degree of the amount of derivatives, so the kth rising factorial of a, b, and c in that way, in that fraction. And then the entire hypergeometric function with the inputs a, b, and c all shifted up by k. And so, yeah, I hope that's clear. It's a neat little fact, and so you can sort of relate any derivative of the hypergeometric function to some version of the hypergeometric function itself. And this actually allows you to define non-integer inputs of the derivative, right? Because all you have to do is think about what the definition of the rising factorial is in terms of the gamma function, because the gamma function is the analytic continuation of the factorial function. So if you recall from the previous video, I was able to show that the nth rising factorial of x is simply equal to gamma of x plus n divided by gamma of x. And because these are both, I believe the word is meromorphic functions, right? They're undefined at only a countable number of points. We have a nice, the only thing you can't really plug in is non-positive integers. And so if you want to define a complex height of rising factorial, it's really easy. You just plug in the complex number there and you evaluate the gamma function, right? So all we need is this definition to be replacing these terms right here. So in this case, x would just be a, b, or c, and n would be k, right? It's not that hard to see. And because this is a nice continuous analytic continuation of the factorial function, all of these are well defined at complex k's. And of course all of these are as well, because you can do the rising factorial of any number you want. You just keep adding 1 to it as many times as the height suggests. Or I guess 1 less than the height suggests. And so all of this is perfectly well defined, and so all of this is well defined too because of this definition here, or this result here, based on how we defined the rising factorial. And so you can have any derivative of the hypergeometric function that you want. So that's pretty cool. I hope that's all clear so far. This is going a lot smoother than the first time I tried to film this. It actually turned out that I ran out of space on my camera on my very large hard drive last time, so I didn't capture most of it, which was kind of a blessing because I made a lot of mistakes in that recording. And luckily, most of them were never caught. Are there any other nice results I'd like to share? Let's see. So let's talk about some specific examples of this function. So we're just going to plug in particular values for a, b, and c, and we're going to see what functions we get out of it by analyzing the Taylor series that we end up with. If we pick b and c to be the same number, so let's pick a to be 1, and we'll pick b and c to be the same number. So we'll just do b, semicolon b, semicolon z. And you'll notice that we have the nth rising factorial of 1, that's just n factorial. So we end up with n equals 0 to infinity, and then if we're plugging in 1 for a, we get the nth rising factorial of 1, which is just n factorial from the previous video. We're getting the nth rising factorial of b, and we're plugging in b for c as well, so we get the same number down there, whatever that is, times z to the n, divided by n factorial. You notice that the two rising factorials of b cancel, and the two n factorials cancel, and we are left with the sum from n equals 0 to infinity, which if you've ever, of z to the n, which if you've ever seen my videos about generating functions, or you know anything about geometric series, you'll realize that this is 1 over 1 minus z. In fact, if you plug in a there, you don't end up with just 1 over 1 minus z, you actually end up with 1 over 1 minus z to the power of a. I'm going to leave that up as a puzzle for you to do on your own. And we'll see how far you get. If we were to plug in other values, let's pick specific values for a, b, and c. Let's do 1, 1, 2, negative z. So we end up with the sum from n equals 0 to infinity of the nth rising factorial of 1, which is n factorial, times, again, the nth rising factorial of 1, which is, again, n factorial. And then we're going to get the nth rising factorial of 2, which is just n factorial again. No, it's, so the nth rising factorial of 2 is, that's going to be the n plus first rising factorial of 1. Right, because instead of starting at 2 and going up n minus 1 steps, we're starting at 1 and going up n steps, so this is going to be n plus 1 factorial. So that's going to be n plus 1 factorial. We have z to the n divided by n factorial. So 2 of the n factorials cancel. This cancels with that. And then n factorial divided by n plus 1 factorial is just n plus 1. And so that's going to give us the sum. That was not fake. From n equals 0 to infinity of z to the n divided by, negative z to the n. Should have written that before. Negative z to the n divided by n plus 1. Raise everything up by plugging in n minus 1, and we end up with the sum from n equals 1 to infinity of negative 1 to the power of n plus 1, or I could do n minus 1, it doesn't matter, times z to the power of n minus 1 over n. And you may notice that if we multiply this by z and divide by z out front, you might recognize this as the, what's it called? And if I just make this a plus, you might even recognize that a little bit more. This is just the natural logarithm of, what the bloody hell is it? 1 plus z. So we have the 1 over z there. We have the logarithm of 1 plus z divided by z. So you plug in particular values for the hypergeometric function, you get a familiar function out. So the logarithm of 1 plus z divided by z. And you can do this with just about anything you bloody well want. You can make any function you want, really, with this. And in the next video, we will cover more general versions of this, where we have different amounts of things in the left spot, different amounts of stuff in the middle spot, and of course the z is always the same. If you enjoyed today's video, please subscribe, give it a like, leave a comment. Any constructive criticism would be completely welcomed. Please tell your friends and your family about this channel. I'm trying to make it grow as big as possible. We finally passed 1,500 subscribers a little while ago. I didn't feel like that was large enough to do any sort of fanfare. But once we get to 2 grand, I'll do a live stream for those who give a about that. In the meantime, thank you very much for watching. I hope this was enjoyable. I hope to continue going into this. Though next week we're going to go back to real analysis for a little while, because I'm itching to continue that series. I told you I would go through the book. I am going to go through the book. And we're going to be doing it lecture style like this, so perhaps it'll be a little more personable and personal now that I'm sort of on camera the entire time. So thank you very much for watching, and goodbye.